Hello, this is the lecture about quantum ideal gases in our course on statistical physics. And this lecture will be structured in 3 points. First, we will look at the grand canonical ensemble, which is, we have seen already the canonical ensemble and the microcanonical ensemble. So this is the third one that will describe systems in contact, systems that exchange particles with a reservoir. And is going to be a very important tool, a crucial tool for quantum ideal gases, which is the second point. And we will see the two types of quantum gases, which are fermions and bosons. And finally, we will focus on fermions. Bosons are also interesting, but fermions are important because electrons are fermions, and electrons in metals and semiconductors behave as quantum ideal gas of fermions. And one of the key concepts there is the Fermi function, which is something that we will use also in the future. So let's say that one of the goals of this lecture is to understand and the Fermi function. Okay, so let's start with the grand canonical ensemble. As I said before, this is the ensemble for a system that it is in contact with a thermal bath. And we have seen already the canonical ensemble, that it was, we derived the canonical ensemble as a system exchanging energy with a thermal bath. Now we will add as well the exchange of particles. So we have this system that exchanges particles and energy. Of course, if you exchange particles, you have to exchange energy somehow. So and what is the ensemble that describes this system? Well, as we have done with the canonical ensemble, the global system is described by the microcanonical ensemble. So every microstate of the global system with some energy, which will be the total energy of the system plus the bath, it has the same probability to be visited. So, but we are now interested only on the system. So we are going to ask for the probability of finding the system in a given microstate. So this is X will be, as always, the microstate of the system. And now the number of particles in the system is also a random variable. So we have to ask ourselves about the probability to find a certain number of particles. And this is going to be N, capital N is the number of particles in the system. So we have this probability, which is a mixture of probability, this density, because X could be discrete or continuous, and N is discrete. So rho is going to be a mixture of probability, this density, and probability distribution. And in quantum systems is going to be a probability distribution. So what is this probability? So we have, as always, we have the ratio of the number of states, or the volume in phase space, compatible with what we are looking for. In this case, this is you see, this is the number of states with a given in where the microstate of the system is fixed, and the number of particles of the system is fixed. So what is the number of states? Is we only have the freedom to change the state of the bath. So the number of states in the bath with some given energy, and the energy is fixed because the total energy is constant. So the energy of the bath is going to be given by the total energy minus the energy of this microstate with this number of particles. And the number of particles of the macrostate of the bath is also determined because it's in the total number of particles, which is constant, minus the number of particles in the system. So omega, remember that we saw this when we studied the microcanonical ensemble. Omega is the number of microstates, or in phase space, the volume in phase space, compatible with this energy and with this number of particles. So this is the number of states compatible with x and n, and we have to divide by the total number of states, which is we will have also some omega for the total system with some total energy and total number of particles. Okay. Now we can express this in terms of entropies. Remember that omega is related with the entropy. Is the omega is the exponential of the entropy. So now we have this expression. We can eliminate. I've written here proportional to. So this is just a constant, the total number of states. This does not depend on the dummy variables x and n. So the only dependence on x and n comes from here, from the entropy, which is the entropy of the bath. Okay, so we have the entropy of the bath evaluated in this energy, which is determined by the microstate of the system and this number of particles. And now, exactly as we did with the canonical. With the canonical, when we derive the canonical, we can take this entropy and make a Taylor expansion. So we have this is small compared to the total energy, and n is small compared to the total number of particles because the bath is a big system, it's a reservoir. So we can expand, and then in the expansion we get first the zero order, which is evaluate the entropy in the state, in the reference, I mean in the total energy and total number of particles, and then we have the Taylor expansion. So we have the derivative with respect to the energy of the bath, and now evaluate it. We have to evaluate it in minus h, no? And now we have also the derivative with respect to the number of particles, and then we have to evaluate it in minus n. Okay, so this is the sorry. So sorry. So this is the Taylor expansion up to first order, and now we realize that this is 1 over the temperature. This was our definition of temperature, and here we have the derivative of the entropy of the bath with respect to the number of particles of the bath. And what is that? This is something that we define also in the first lecture on thermodynamics. This is minus the chemical potential divided by the temperature. And of course, this is I've not include this at the beginning, but when we say that there is a bath exchanging particles and exchanging energy, this means that the bath is characterized by some temperature and some chemical potential. And of course, if in equilibrium, the system and the bath the temperature will be equal in the bath and the system, and the chemical potential will be equal for the bath of the system. We learned in the first lecture that chemical potential and temperature are equilibrium indexes. Okay, so we now can evaluate the probability that we were looking for, and this is proportional. So we said that this is proportional. So rho xn is going to be proportional to this exponential. And now I will call the constant of proportionality Q. And it's very important. It plays the same role as the partition function in the canonical ensemble. Now it's called grand partition function, and it is calculated by. Let me erase this part. And it is calculated by normalizing the whole probability density. Okay, and it's called a grand partition function. So and if you this is a very important point that. Notice that dx exponential of minus beta hx is the partition function. So we can write this as a partition function. No, this is the integral times the exponential of beta mu n. No, the beta mu n is this part, mu n beta, and minus is plus. So this is the partition functions of n particles. Okay. So this is going to be it's going to play a very important role in this theory of the grand canonical ensemble. So sorry. Okay, so let's start with this the important point, the probability to find the system in a given microstate, no? And this definition of the grand partition function, which is this one here, as in terms of the probability of the partition function of n particles. So this is called the grand partition function. And you see that we have written in terms of the normal or the partition function that we saw in the lecture on the canonical ensemble. Okay, so now we are going to study a couple of course we could do a lot of stuff with this, calculating averages and thermodynamic properties of the grand canonical ensemble, but we are going to focus on a few because the idea is just to have an idea in the very general introduction to the behavior of quantum ideal gases and especially of Fermi gases. So we will only sorry, this is for n particles. So we will only focus on the average number of particles because now is the new feature of this ensemble is that the number of particles is random. It's a random variable, so it is worth it to calculate the average, and the average is of course we have to sum. As I said before, here we have a kind of mixture. The probability density, the probability of finding microstate X and a number of particles is a mixture. This is a density in dx, but it is a sum in n. Okay, and now we multiply by n to find the average of this quantity. And the trick to calculate this is the one that we have already done in the canonical ensemble and in many instances. Is we write this we can write this as the derivative. You see, if I make the derivative of this with respect to mu, I get a beta n, so I can write this n as a derivative of this quantity, and then the q goes out of the I can take out of the sum and the integral the q, so I can get this expression, which is very similar to what the calculation we did in the canonical ensemble to find the average of the energy. And now this is the log, this is kt and the derivative of the log. So very similar to, and now it's the derivative with respect to mu. So you see also that kt log q is going to play an important role. It's actually, you remember that kt log z, the partition function, was the Helmholtz free energy. Now this is another thermodynamic potential. It's called the grand canonical thermodynamic potential, and it has very important properties like the Helmholtz free energy. Okay. We will show now in an example how all this works. Another important stuff is that this kt log 2 is, as I said, is like a potential. So one can show, we will not do this in detail, that the pressure, for instance, and other magnitudes of interest can be written as the derivative of this potential with respect to the volume. But this expression, the pressure as a function of the grand canonical partition function, the grand partition function, is interesting because you see this is a potential, so it's an extensive quantity. But look at the variables. So Q depends on the temperature, the chemical potential, and the volume. You see that the entropy, the natural variables of the entropy are energy, number of particles, and volume. Then we went to the free energy. The variables, the natural variables of the Helmholtz free energy are temperature, number of particles, and volume. And now we replace the number of particles by mu, because the number of particles is no longer a fixed parameter. Now it's mu what determines the number of particles. So the natural variables of Q are temperature, chemical potential, and volume. And you see this from these three variables. The problem is that you cannot. How can you get an extensive quantity? So the only extensive quantity here, T is intensive, mu is intensive, so this don't grow with the size of the system. The only one is the volume. Okay, so then the only way to get an extensive variable just with another extensive variable is the only possibility is that log of Q is proportional to the volume. But if log of Q is proportional to the volume, then this is the pressure is so the pressure is the proportionality constant. Okay, so the only way to do this is that the log of Q is PV. So this is another interesting property of the grand partition function. We have seen only this, but of course we could do fluctuations of the number of particles, fluctuations of energy. There are many things that can be calculated, but we will restrict ourselves to these two things. Okay. Now let's see this in an example. Before, I want to mention something which is also important, that okay, we have introduced this the microcanonical, the canonical, and the grand canonical as describing different situations. No, microcanonical was the ensemble that describes an isolated system. The canonical describes a system in contact with a bath, but only exchanging energy with the bath. And the grand canonical describes a system in contact with a reservoir or a bath, but exchanging particles and energy. Okay, the interesting thing is that in the when n is large, so if you have a large number of particles, this is by the way, this is called the thermodynamic limit in the textbooks of statistical physics, and there is a lot of work on how to define correctly the thermodynamic limit. The three ensembles are identical, so they only, you can imagine that the difference between one and another is that they exchange some quantity. So this quantity becomes random, no? Energy in the case of the canonical, and energy and number of particles in the case of grand canonical. But fluctuations are very small in this thermodynamic limit for n very large. So then the three are essentially equivalent, and this is what allows us to study quantum ideal gases. That we could study quantum ideal gases in the canonical ensemble or even in the microcanonical, but it turns out that it is very hard or not possible to analytically calculate the partition function of quantum ideal gases, and it turns out that it is much easier to calculate the grand partition function. So this is why for quantum ideal gases we will use the canonical ensemble. Okay, let's move to, let's explain all this in an example. So as an example, I will use the let's think of the classical ideal gas. Okay. In the classical ideal gas, well, first we start with the partition function, and the partition function, well, it's remember it's the partition function of just one particle raised to the power n and divided by n factorial. This was to avoid the Gibbs paradox. So we can introduce this in the expression for the grand partition function. Remember, it's just this expression, and now you can, if you look at this thing, this is some number zeta 1 exponential of beta mu to the power n divided by n factorial. This looks like a difficult series to sum, but it is actually very simple, because it is, if you remember, the Taylor expansion of the exponential is the same, has the same structure, some number to the power n divided by n factorial. So by identifying this, we can immediately write that this is the exponential of zeta 1 exponential beta mu. It's a bit strange, this formula, to have exponential of exponential, but remember also that the what has a real physical meaning is not q, but it is its logarithm, and if we take the logarithm, we immediately get z1 exponential of beta mu. And z1 is the partition function of a single particle, which is something that we have calculated or we have studied in the lecture, in the previous lecture with the canonical ensemble. Okay. Let's see some properties. For instance, we mentioned the number of the average number of particles. We mentioned that this is kT, and the derivative of this with respect to mu. If I make a derivative with respect to mu, I get beta. So I get z1 and beta and then the exponential. And beta cancels with kT, so I get this result that the number of particles is, of course, adimensional. So z1 is adimensional. In this case, we use this h Planck constant to make a dimensional quantity. Okay, this is one of the first examples of what we have done before. This expression actually is a bit strange to see this expression like that, but it's a familiar one that we have seen before. Remember, if we express instead of the number of particles in terms of mu, we express mu in terms of the number of particles, we get this expression, which we already got this expression in many instances before in the course, like from the Sackur-Totschrodt formula, for instance. Remember that now we can remember that Z1 is for a point for a ideal gas of point particles is given by B divided by lambda to the power 3. Lambda is the thermal wavelength. And if the particles have some internal structure, we have to add also some partition function of the internal degrees of freedom of the particle. Remember that we studied in detail the diatomic molecule and its specific heat. So inserting this into the expression, we get kT log, and the number of particles divided by the volume, we can express it like a density. And now the internal part, we can extract again a kT log of this part. Okay, so, and this will be some free energy associated with this. And here, a small n is the number of particles divided by b. It's the density of particles, but now it's a random variable, remember? And this free energy is minus kT log of the partition function of the internal degrees of freedom. Sorry. Okay. So we recovered the expression that we saw in previous lectures. And finally, another application, if it is interesting, remember from our last slide that log of Q is kT log Q is P pressure times volume. So now this we can from these two equations we can say that PV is kT, and the number of log of Q is the number of particles, so we have PV and kT. So we recover the equation of ideal for the ideal gases. Okay. The second point of our lecture is quantum ideal gases. So we start first by describing the gas. So a gas is a set of number of particles or molecules in a box, and how we describe a gas or the state of a gas. Well, we have to look first at it's an ideal gas, so each particle is in principle independent, although the indistinguishability of quantum particles will induce some kind of correlation between particles. But let's look at a single particle. So we look at a single particle. Each particle will have a set of states. These are the states of a single particle. And this is the building block to look for the state of the whole gas. So how is going to be the state of the whole gas? Well, let's characterize first the states of a single particle. There will be some energy. We can call it epsilon 0, 1, etc. There could be some degeneration, so some of these energies could be equal in the case of gases with a spin. If the Hamiltonian does not depend on the spin, this will have some degeneracy. But let's look at these are just the states with some energies, and the energies could be equal. But we will order the energies in this sense. This will be important in the following. Okay, so this is the description of the state of a single particle. Now, how we describe the state of the whole gas? Well, it's just to put the particles or the molecules in the different states. So we can have one molecule in the ground state, another molecule here, another molecule here, and so on. So for instance, we can have any configuration. So we can have any we can distribute these particles. Each particle can be in any of these states. This is a specific configuration. For instance, this is a specific configuration of 8 particles. No, this is 1, 2, 3, 4, 5, 6. Yeah, 8 particles. Okay. So these configurations, what is how are they determined? So you see that quantum particles are indistinguishable, so we cannot label these particles. We don't know if this is particle 1 or particle 2. So the only thing that determines the state of the global system of the gas is the number of particles in each state. And this is called the occupation number. Okay. The occupation number is the number of states in or number of particles in a state I, and it is usually we will use the notation n sub I for this occupation number. So it's the number of particles in state I. Okay. So a configuration will be just to specify the occupation number of the whole of our gas, of all the, so these occupation numbers, no, for all the states. But we have a condition, because if our gas has n particles, so the condition must be that the occupation numbers must be sum n. Okay. Another condition, what is the possible values of n of this occupation number? Well, here we have the main distinction in quantum gases. We have 2 types of particles, bosons, which have spin, integer spin, and they are indistinguishable, but they can be distributed along these levels or these quantum states in any way. So the occupation number can be 0. This means that the state is empty, the state I is empty, or can be 1, 2, etc. Or all the particles, the n particles, could be in this state. So any of these values are possible, and any set of values with this condition and with this the occupation numbers taken on these values is a possible configuration. But we have also fermions. Fermions are particles with a semi-integer spin, like actually, most particles like electrons, protons, and neutrons, and so on, are fermions. And in fermions, we have the exclusion principle, the Pauli exclusion principle, which tells us that there is 2 fermions cannot be in the same quantum state. So this means that here are states, not levels. So the states don't have a degeneracy. This is, and then the state can be either empty or occupied by only 1 fermion. But we cannot have more than 1 fermion in a state. Okay, so this is how we describe the state of a gas, or not even a gas, any system composed by indistinguishable particles, bosons or fermions. And finally, the total energy is just the total energy will be each state has an energy epsilon sub I. So if I have n particles in state I, this is the number, the contribution of those particles to the energy, and if I sum over I get the energy of this configuration. So I have perfectly determine the state of a system, its energy, and so on. So we can now try to apply statistical physics. So the first could be try to apply to calculate the partition function. So the partition function, remember that it is given by, for n particles, is given by this expression where we sum over all possible configurations, and we sum over all possible energies, and this is exponential of minus beta. In the case, as we have already characterized the global states of the gas by these configurations, so we will have that now the sum over states is a sum over configurations, okay? And now the exponential of minus beta, the energy is just the expression that we have seen in the previous slide, which is this one. Okay, this is the partition function, but we know that these configurations must obey this constraint. The number of particles is equal to n. And this is a problem because this makes this calculation very hard to do. So it's not possible to calculate this sum with this constraint. Okay, it's a very hard combinatorial problem which has no solution in general. But it turns out that if we look at the macro, at the grand partition function, remember the grand partition function is given by this expression. This is what we studied in the first part of the lecture. And if we introduce the partition function here in this equation, so what we get is the following. We have the sum over configurations, and now I introduce the partition function. Okay, look at this. This part is this exponential, and now I have this in this part n. Remember that n is given by this expression, so I can replace n by the sum of the occupation numbers. And now I have this expression here where capital N goes from 0 to infinity, and then for a given n, remember that this ni is still has to obey this constraint. Just to specify this constraint, let me put here an n to specify that these configurations must obey this condition. Okay, and we have the same here. So this sum depends also on n. But look at these two sums. Since n here goes from 0 to infinity, this constraint, in fact, can be any number now. So we now we can replace these two sums by a single sum where there is no this constraint. Okay? So we now have just a single sum with no constraints. Sorry that I wrote too much. So now I can and I just here for this I just put everything under the same sum. So this is ni epsilon I minus mu. You see that there is a plus here with a minus mu. So we can replace now by calculating the grand canonical partition, the grand partition function. We got rid of this constraint which made this calculation very, very hard or impossible to do it analytically in general. So now we have this, and this is much easier to calculate. Why? Because you see that the exponential of this sum, this is a product of exponentials, and now the n's are completely free. So I can factorize the sum. I can have a sum over the first occupation number, I can have a sum over the second occupation number, and so on and so on. Okay. And now this is completely factorized, so I can you see that this is a completely independent sum. This is the completely independent sum over the occupation number of each of each state. So now let me rewrite what we have here. Okay, so this is the product of these guys, of each of these sums. Okay, and now, and this is the nice thing of this calculation, this sum is very easy to do, because remember, what is Ni? Ni goes, if we have bosons, Ni goes from 0 to infinity. No, from 0 to n before, but now n is it no longer appears, so it's from n to infinity. So this is you see that this is a geometric progression, or geometric, and we have the sum of a geometric progression, and this is very easy. This is just 1 minus 1 divided by 1 minus the ratio of the progression. So we can calculate this, and for fermions, it's even easier, because for fermions, remember that the occupation number can be only 0 and 1. So this sum over Ni only has two terms, n equals 0 and n equals 1. So we have, for n equals 0, we have 1, and for n equal 1, we have the exponential of minus beta, the energy minus mu, minus the chemical potential. So this sum is easy to do, and now we can replace and replace it here. But remember that what it has physical meaning is not q, but it's logarithm, and this is even better for us, because we can replace this the sum of the product by a sum. So now we have the sum. Let me split into two, because we have two results for bosons and fermions. Now I have the sum of the logarithm of this guy. The logarithm of this guy is minus the logarithm of the denominator. So I have the logarithm of the denominator. That's it. And now for fermions, I have the log of the sum. The log of the sum is the log of this guy, and I have a sum over states of the log of this. And this is an exact calculation, and now I only need to know, of course this is very general. I've not to apply this to for instance a gas in a box. We need to know the epsilon I. Remember that it is the energies of the eigenstates of the Hamiltonian of a single particle. So this is something that we can easily do, like solving the Schrödinger equation for a single particle in a box. And then for a gas, we have this expression. It is customary to put this, let me erase this part, this thing, and it's customary to write these two with a parameter theta. You see, we can write the two expressions. We can put it in a single expression with theta. Theta is something which is a parameter that it is -1 for bosons. So you see that I have this minus and this minus here, and it's +1 for fermions. And you see that is plus, so I have the 2. And this way of expressing the grand partition function is useful to calculate the classical limit. Of course, quantum gases at some point should behave as a classical ideal gas, because we have solved the partition function for the classical ideal gas, and from it we have derived the specific heat and also the equation of state for the pressure and the volume. We know that in these expressions are consistent with experiments. So the quantum ideal gases at some point they should converge, no matter if they are bosons or fermions. They should behave as a classical gas. So we expect that this log of Q in some appropriate limit, which is called the classical limit, will approach the log of Q that we calculated just before for the classical ideal gas. And this is true. What is this classical limit? Well, I will not go into details, but the main idea is that the chemical potential is much smaller than all the energies of the system. If the energy is the ground state, sorry that I use epsilon 0 for the ground state, now it's epsilon 1. So if epsilon 1 is the ground state, the energy of the ground state, sorry, then mu, which is usually negative, must be much smaller than this energy. Then, if this is true, in this sum, you see that mu is this epsilon minus mu is going to be very big, and because of this minus sign, this exponential is going to be very small. So this allows us to do the following. We can here we can use this the expansion of the logarithm. And then when we do that, look at this log will be theta, the exponential, and theta times theta is always, it doesn't matter if we have bosons or fermions, theta squared is always equal to 1. So here we have that this is the sum of this. And now immediately you recognize that the sum over all the states of exponential minus beta epsilon I is the partition function of a single particle. So we have the partition function of a single particle times exponential of beta nu. And you immediately recognize here the classical result that we obtained before. Okay, so yeah, in this limit, we recover the classical behavior of the gas. Let's explore a little bit more what are the physical meaning of this limit. It's remember the classical expression for mu. Now that we know that we recover this classical limit, we can. It's a little bit a circular argument, but we can to interpret this limit, we can use the classical expression for mu, which was this one. Okay, this is mu for a classical ideal gas with no point particles. Lambda, capital lambda, is the thermal wavelength. And if this is for an ideal gas where the ground state has energy 0 or close to 0. In the case of quantum particle, we cannot have 0 energy because of the uncertainty principle, but this is almost 0. So this condition implies that this is very negative. Okay, this is very negative, and this means that the argument of the logarithm must be very small. The argument is sorry. The argument is positive, so this is a density, number of particles per volume. This is lambda, is a positive quantity. This is positive, so when we say much smaller than 1, we mean that it must be very small, very close to 0. And what does this mean? Okay, this is the number of particles per volume, per unit of volume. And this is the thermal wavelength. Remember that the thermal wavelength is the Broglie wavelength associated to the thermal energy kT. So it's the wavelength of a particle that has an energy kT. It's like the quantumness in terms of length of a particle with energy kT. So what does this mean? This means that the density must be much. Let me erase this one. This must be much smaller than this one, and this means that the gas must be dilute. I mean, the density must be low. So we recover the classical limit for low densities, and this low density has also a very nice meaning. If it means that if I have two particles, the density must be low enough in order to have the two particles at a distance which is much bigger than lambda. Lambda is a bit like if each particle, because of the quantum nature of the particles, has a wave associated, the length of this wave is lambda. So now this classical limit means that the distance between the two particles, this distance d, must be much bigger than lambda. Okay, so this is the idea. So to have quantum gases, we need either to have very high densities or very small, very large lambda as well. This is another possibility. This is one of the conflicts. The difficulties to get, for instance, Bose-Einstein condensates was related with this inequality here. Okay. So let's go on. So I've calculated log of Q. I've used the classical limit, but now that we have an expression for the log of Q, we can calculate all the thermodynamic properties of these quantum ideal gases, ideal gases of bosons or fermions. So one of the most important properties is the number of. Let me rewrite again the expression for log of Q. And one of the things that it is more interesting is to calculate the average number of particles. Remember that we wrote this as as KT log Q, the partial of log Q. And well, it's going to be better to write this in terms of beta. So now we are going to do this calculation. Here is to calculate the derivative. The derivative of the log is 1 divided by the argument. So in the case of bosons, we have 1 divided by this. And now in the numerator, I have to put the derivative of the exponential, which is with respect to mu. So there is a plus, but there is a minus here and a minus here. So at the end, I have a plus the exponential. And it is customary to write this to multiply by the exponential both in the numerator and the denominator, and then we get this nice expression for the number of particles. And this is valid for bosons. Okay, and for fermions it's very similar. Now we have the derivative of this, the log of this. So I will have in the denominator this thing, and in the numerator I will have the exponential. And I can multiply again and get this for fermions. Okay, this is the number of particles. This is nice, but you see the number of particles is expressed in both cases as a sum over the states of the single particle. So on the other hand, the number of particles is equal to the sum of the occupation numbers. I will not present a proof of this, but it is immediately we can identify this as the contribution to the number of particles of a state I, and this is nothing but the occupation number of a state I. So these two things will be the occupation numbers, this quantity and this quantity, but now the occupation number is random, so it will be the average occupation number. Okay, so for bosons, this is, and this is going to be one of the, of course we could do more things like calculating the equation of a state, which is very interesting, how the You remember PV equal NKT, no? The equation of ideal gases, how it's modified when we have bosons and fermions. This is interesting, but we will just, as I said at the beginning of this lecture, we are going to focus only on the most important things. So one of the most important things is this average occupation number. Actually, the most interesting phenomenology of bosons and fermions can be explained just by using this average occupation number. For instance, for bosons, we will not look at in detail. I mean, we will just mention something for bosons. For bosons, what it is interesting is that this occupation number, you see that in the denominator we have the exponential -1. What happens if this is 0? Then we have 1 minus 1. This is infinity, and this could happen. This happens when mu, which is usually, as we said before, is usually negative, but it could be equal. At some point, it could be equal to the ground state, or it could tend to the ground state. It cannot be equal because my gas has m particles. No? Although n is a random variable, we can remember that the grand canonical and the canonical are equivalent in the thermodynamic limit. So if I have a number of particles, this is still true, even if n is not random. So if I have n particles, this cannot be, this is always positive, and this cannot be 0, exactly 0. But we can have this limit where mu goes to the ground state. And what does this mean? This means that the occupation number of the ground state goes to infinity. And so the occupation number of the ground state diverges. Of course, the occupation number cannot be bigger than n, okay, because we have this sum. But this means that the occupation number of the ground state becomes as large as the size of the system, and this could happen. And this is the famous Bose-Einstein condensation. And this is, of course, this has created a lot of literature. And in '95. It could be realized in the experiment. This was predicted by Bose and Einstein in the 20s, but in '95 was realized in the lab, and since then the Bose-Einstein condensation is a big topic in experimental quantum physics. But we are not going to explore this. This is something that you can find in books like Huang's books and so on. Okay, this is for bosons. For fermions, we are going to look a little bit farther. And for fermions, the occupation number, let me erase that. The occupation number is you see, is a function. Is a function of the energy of the state I. So this function is very important, and it's called, let me erase that, it's called the Fermi function. It's this and the expression is this is the Fermi function. And as I said at the beginning of the lecture, this is going to be the third point that we are going to study, because I think the phenomenology is interesting, and it has a lot of applications, and among those applications we will study one of them in the future. Okay, so let's go to the last point, which is the Fermi function. So here you have the Fermi function, and remember that the Fermi function, the Fermi functions tells us how many particles do I have in each state. This is the important thing. Okay. This is it's this, but it tells me this is the important interpretation of the Fermi function. So what is the aspect of the Fermi function? Let me draw it. It's like something like that. So here it's as a function of the energy, and it's like a sigmoid function, and it's at mu. You see that at mu the Fermi function, this is 0, so I have 1/2. So this is 1/2. And for big values of epsilon of the energy, this is very big, this exponential. So 1 over something very big is very small. This is exponentially decaying. And for epsilon small or epsilon 0, this is for epsilon 0, for instance, is exponential of minus beta mu plus 1. Mu, as said before, is mu is very negative, so this is very positive, and then this is very big, and this is well, this should be very small, and I think I have a mistake here. Anyway, this is almost 1 when epsilon is when epsilon is far on the left from mu. Actually, what it is important here is epsilon minus mu. Here, epsilon minus mu is very negative. Okay, very negative. So this is almost 0. So this is not for the important thing is the difference between epsilon and mu. And here in this point, I'm far from mu. So epsilon minus mu is very negative. And this is so for Fermi gases, mu is not actually no. This was my point. For Fermi gases, which if we are far from the classical limit, mu, we will see in a moment, mu is very positive. Mu is much bigger than the ground state. The ground state usually is epsilon equal to 0. Okay, this is how it looks, the Fermi function. And now, so this is almost equal to 1. And you see that we have the states of the system according to the energy. This is the occupation number. So we have a lot of states that are with an occupation number which is almost 1. So it is full occupied. So we have a full occupation here in this area. And there, for high energy, we have that the states are empty. No, this is epsilon. This is the occupation number is 0. So we have empty states. So this is how an ideal gas of fermions behaves. At some temperature, the states below the chemical potential are occupied, and the states above the chemical potentials are empty. And we have this transition here, and this transition where we have half occupation, let's say, or not total occupation or total emptiness. This is a small interval. Well, it's an interval of energies which is of order kT. You see, when we have kT, when epsilon minus mu is of the order of kT, is when this exponential has intermediate values. Otherwise, it's either 0 in this area, or this exponential is infinite in this area. Only for epsilon minus mu of order kT, we have this transition. Okay, this is the picture. And it is interesting to see this at 0 temperature. What happens at 0 temperature? At 0 temperature, this interval becomes infinitely narrow. So we have that the Fermi function is a step function. It's 1 here. Here again, well, t going to 0 is beta infinity. So this is infinity. So whenever we have a positive difference, this is going to be infinity. If we have a negative difference, so if the energy is below mu, we have a negative difference here, and this is 0, and this is 1. So we have 1 and 0. So we have occupation and 0. We will see that this is clearly at T0 the gas is in the ground state. Remember in lesson 1 we saw that a system in contact with a thermal bath at 0 temperature, the equilibrium state is the ground state, the minimal energy state, and this is the minimal energy. The exclusion principle. The minimal energy will be to have all the particles in the ground state, but because of the exclusion principle, we can just have one, or the degeneracy of the ground state. So we have to feel the different states. We will see this in a moment in more in detail, and we feel all the states with a small energy, and up to some value, which is the chemical potential. Okay, and this value is very important. This is the chemical potential at temperature 0, and it's so important that it has a name. This is the Fermi energy. It's usually denoted as epsilon F or sometimes epsilon mu F, and this is the Fermi energy. Okay, and we will see in a moment what is the interpretation and so on. How we calculate the Fermi energy? Well, here is the interpretation. So we have here the levels. This is what I was mentioned before. Suppose that these are the levels of a single particle. Remember that these are levels of a single particle, no? Epsilon 1, epsilon 2, and so on and so on. So the idea is that the gas wants to be in the ground state. So what is the ground state of the gas? So we have to put particles in the states with the lowest energy, but we can only put one. Or well, if there is the degeneracy, we can put more. But let's think that these are states, not levels. They are states, so we can only put one. And then the next particle should be in 2, and the next in epsilon 3, and so on and so on. So we put all our particles in the first n levels, and this is the ground state, and this is what represents the Fermi function. You see, and those states will be empty. So here, this is the way to calculate the Fermi energy. Is just to count how many states do I have below a given energy, and to make this equal to the number of particles. Usually in gases we have we have a discrete spectrum. This is the eigenvalues of remember, this is the states of a single particle. So this is the eigenvalues of the Hamiltonian of a single particle. Usually when we have a particle in a box, we approximate these discrete levels by a continuum. So instead to see how many states do I have below a given energy, I have to make an integral of what it is called the spectral density. Spectral density is the number. This times the epsilon is the number of states in an interval epsilon plus the epsilon. So if I integrate the spectral density over some interval of energies, I get the number of states. This is the number of states up to some energy epsilon f. And then because of this interpretation, this should be equal to the number of particles. See, here I don't put average n. As I said before, we can apply all these in the limit of n large to the situations where the system is in contact with a reservoir or just with n is fixed, because the canonical ensemble and the grand canonical ensembles are equivalent in this limit. Okay, so if one does this, this is possible to do, for instance, for fermions or electrons, for instance, in a gas. Actually, this is valid for particles with spin 1/2. One can calculate. This is you look that this is an equation. So n is known. This is given by the problem, for instance, by solving the Schrödinger equation in a box. So this is an equation for epsilon f. So we can extract epsilon f, which is what we have done here. And if you make this calculation, this is in any book of statistical mechanics, but I will not do it here. Is given by this. where n is the density of particles. So the number of particles is n divided by volume. Here the volume appears, so n divided by the volume is this density. And this is the Fermi energy of free electrons in a box. Okay, let's copy this in the next slide. So we have the Fermi function, which has this form, as we have seen. And also at zero temperature, the shape is like a step function, and we have, well, we didn't calculate, but we have written the expression for the Fermi energy for electrons with some density. Okay, so now we are going to apply this to a very important example, which is electrons in metals. So suppose that you have a piece of metal like this, and the metal consists of atoms which are distributed in a lattice. So these red dots are the atoms, the nuclei actually of the metal, and it's a crystal lattice. And then in metals we have, or in conductors, we have electrons. Most of the electrons, for instance, in iron, are bound, are localized around the corresponding nucleus, but there are some electrons, here are these white dots, which are called conduction electrons. And these electrons can move all over the metal, and so they are like a gas. They are a gas, and one can in normal conditions these electrons are an ideal gas. Of course, they collide with the atoms of the lattice. There are collisions between these conduction electrons, and those collisions are very important to calculate transport properties like resistance or heat conductivity. But for equilibrium, when the metal is in equilibrium, the conduction electrons behave like an ideal gas, and they are fermions. So we have an ideal gas of fermions, so we can apply all this theory. We can calculate the free energy, and it will be the distribution. The electrons will be distributed with the Fermi function. So let's calculate the density. So sorry, let's calculate the density. Remember that this is the density of molecules in the gas. So the number of molecules divided by the volume. In this case, the molecules, let's say the particles that are in the gas, are the conduction electrons. And usually we have 1 or 2 conduction electrons per atom. So to calculate how many conduction electrons we have per unit of volume, we have to calculate first how many atoms do we have per unit of volume. And this is nothing but the density of mass divided by volume, which is something which is for metals is more or less is something that don't depend so much on the temperature. Of course, we have that the expansion the metal expands when it's heated up, but the density of which is volume, mass divided by volume, is more or less it doesn't change so much in a broad range of temperature, and the atomic mass is constant. So this is a number which is more or less the same for a broad range of temperature. So this is the density of atoms. Now we have to multiply to get the density of conduction electrons by the number of conduction electrons per atom, which, as I said, for instance, for iron is 2. and for other metals is 1. So this depends on the electronic structure of the atoms that compose the metal. So let's calculate this for iron. So for iron, we have that the density, you can look at this in any book, is around 8,000 kilogram per square meter, per cubic meter. Sorry, the atomic mass, which is this one, also in kilograms, and then, as I said before, the conduction electrons is 2. So we can introduce this. For instance, you can use Wolfram alpha, which is very nice to introduce physical constants and units, and then we get the density of conduction electrons, which is of the this one. It's like 1,000, the Avogadro's number, and now we introduce this in the formula for the Fermi energy, and we get the following that the Fermi energy is around 11 electron volts. There are two interesting comments on this value. The first one is that let me erase this one, is that if you calculate kT, the thermal energy, for instance, for 300 Kelvin, this is around 0.03 electron volts. So we see that the Fermi level is like 1,000 times the thermal energy, and this means that this interval is very far from the origin. So if this curve for many purposes will look, this is like this is very small, this distance, so it will look like 0 temperature. So for electrons in metals, it's very surprising, but the room temperature is almost equivalent to 0 temperature. So this can be justified by calculating properties like the pressure and things like that. But the main idea is that the Fermi level is so big compared with kT that we can replace this curve by a step function. Okay, so we are very far from the classical limit that we have seen before. Where is the classical limit? The classical limit will be mu very negative, actually. So if epsilon equals 0 is the ground state of my gas, well, it's always a bit larger because of the uncertainty principle, but let's say that the ground state starts here. So the classical limit is that mu is very far from mu is very negative, and the curve will start here. And but this is for densities which are much smaller than the density, the typical density of particles in the metal, of conduction electrons in the metal. Okay. So the first important conclusion is that in metals, electrons are more or less distributed like that, or at higher temperatures like that. But at room temperature, the Fermi function is almost it can be approximated by a step function. Okay. So the second phenomenon that I want to, the second point that I want to discuss is just what happens when we put in contact two metals. So we have the iron. Sorry, that I will erase this part. So we have calculated for iron, the Fermi energy is 11 electron volts. You can do the same calculation, for instance, for copper. So for copper, it's interesting that for copper, if you go to the Wikipedia or any book on the properties of metals, this is very different. And this one, copper has a different atomic mass, but the density of atoms is very similar. It's almost the same in copper and iron. So the big difference is in the number of conduction electrons, which in copper is 1. So this will be a factor 2 here, a factor 2 to the power 2/3, and this is more or less 7 electron volts. So comparing these two Fermi energies is interesting, and we will do it at 0 temperature. So remember, what is the meaning of the Fermi energy? We have the levels, the states of a single particle. So these are states of a single particle for iron and for copper. And what we do at 0 temperature is the system wants to be in the ground state of the global ground state. So we put our electrons in the different states. Because of the Pauli exclusion principle, we cannot put more than one. There is a degeneracy, of course, because of the spin, but there is we have to fill these states one by one. And for iron, it's clear, because the Fermi energy is higher. We can fill it up to the level with 11 electron volts, and here we can fill these states up to 7 electron volts. So this is how a piece of iron and a piece of copper are when they are in equilibrium. Now suppose that I connect these two with some cable or some I connect with some conductor here. So now electrons can move. Conduction electrons can move from iron to copper or from copper to iron. And what will happen? Well, now the global system wants to be again we are at 0 temperature, so the global system, as we saw in the first lesson, the global system tries to go to the ground state of the global system. So now what these electrons can do is to move here, and they will move to levels with a lower energy, and the energy will lower, if we have this motion. And what is this? Okay, this is nothing but current of electrons. This is electrical current. So if we connect the two, there will be an electrical current moving from iron to copper. Okay. And this current will last until the two chemical potentials are equal. So we see again the interpretation of chemical potentials. Remember that we studied in the first lesson. This is like temperature. For energy, the chemical potential is the same for particles. So here, the chemical potential is higher in the iron than in the copper. The chemical potential at 0 temperature is the Fermi level, Fermi energy. So there will be a transport of particles, a current, until the global system reaches equilibrium, and equilibrium is that the two chemical potentials are equal. Now, these chemical potentials will be different from the energy. This Fermi energy that we have calculated here is for neutral iron and neutral copper, because we are assuming that there in this expression we are assuming that there are two conduction electrons for each atom. So this means that the piece of iron is neutral. There is no charge. But when we connect the iron and the copper, then this current will charge negatively the copper and positively the iron, and the chemical potentials will be no longer the Fermi energy that we have calculated here, for instance. Okay. So this is a nice phenomenon that also it's interesting, because first we recover this idea of the chemical potential as a equilibrium index, that if there is a difference of chemical potential, there will be a flow of particles. And second, actually, if you think of this argument, we can just understand this argument without any need of the grand canonical ensemble or any need of the even statistical physics. We only just need that the system wants to be in the ground state for 0 temperature. For this expression, we do need all the calculations that we have done in this lecture. Okay, so this is a nice phenomena, and just to finish, well, this is the famous Volta pile. So Volta in 1799, he put I think he did it with copper and zinc, but he put pieces of metal separated by some wet cloth, which will be this that allows this transfer of particles. He found this current that could last for large for very long. Okay, so this is all for that we wanted to discuss about quantum ideal gases. Thank you and see you.